Hello, everyone. We'll just jump into it. There's a lot of stuff that kind of had to get left out because it's a comprehensive topic. But if you guys have any questions, there's an email and a Twitter handle, and you can find me after the talk. So we were missing a slide, but about me, I work at F5 Silverline as a SRE engineer. And one of the things we do is software as a service, so DDoS mitigation and web application firewall stuff. And we know that we have to monitor our network in order to detect problems before they occur and help have a faster time to resolution. So we offer security as a service. We do this with proxies. So we have a global proxy network that spans the globe. We have some megapops in various regions, and then we just released RPops. We use an Anycast network to direct this traffic to these proxies, and also wide IPs and GSLB. And the transit for this relies on public transit providers, and of course there can be things that go wrong there, and so it behooves us to keep an eye on that. So what we're up against, we're deeply invested in our customer support. Our configuration is constantly in flight, and that brings opportunities for failure. Outage inquiries can arrive at our NOC or our SOC lacking technical information that we need to troubleshoot and resolve the issue. And our global HA deployments create kind of divergent behavior where traffic in the US can go to a different place versus Europe. So we need to keep that in mind. And we have the requirement of collecting network vitals from an end user's perspective, and we need to do this regularly at very tight intervals for thousands of entities. And so we have there are a number of very good canned solutions. Pingdom, for example, Thousand Eyes is excellent. But at scale, it becomes very costly for us to use that. If we're talking about monitoring tens of thousands, hundreds of thousands of proxies, the cost adds up very fast for us. And so we got to thinking, can Zabbix do this? We use Zabbix to monitor our infrastructure already. The low-level discovery mechanism in Zabbix is fantastic, and it's declarative. User parameters allow you to execute arbitrary logic, and then the orchestration is centralized into the server. Proxies and agents can offload work from the server, which is great. And Zabbix containers are now available as of 4.0 in containers, so that's a plus. And it has mechanisms for handling problem creation and alerting already built in, and also a GUI. So that's all great to get for free. So we developed something we call Cosmos, and it's Zabbix meets distributed scheduling. And so it kind of looks like this. The big picture is that Zabbix agents monitor apps and not hosts, which is traditionally Zabbix's stick. It monitors like an entity, a network device or something like that, returns health stats. We want to monitor web applications. We use LLD to install and remove work into the system. The user parameters wrap common Unix utilities like curl and dig and stuff of that nature. And then we send stuff back to Zabbix via traps. And we also, in parallel, generate rich JSON documents that go out to Elastic. And then Redis serves to hold placement state and also buffer documents. So this is built into Amazon. We have a core node which handles several services like the Zabbix server, the GUI, Logstash, just a whole bunch of support services. We have two databases, Postgres for the Zabbix config, and then we're using the Elasticsearch as the history backend. So we've got a cluster here. And then we've got two Redis instances, one called Factor, which holds all the placement state and facts, which we'll get into. And then Buffer, which holds those rich JSON documents as they're waiting to go into Elastic. And then we have many T3 micros that run numerous Zabbix agents. And so the way we scale, at scale, we can scale our presence by just adding a region in AWS. We have a whole bunch of Terraform and Ansible that can spin this up in an automated fashion with no human input, which is great. You just go in and add a couple of stanzas into the Terraform, and you're off to go. Jenkins controls all that. We don't have time to talk about that right now. Increasing capacity in a specific region, we just request more T3 micros and then spin up more Zabbix agents on those T3 micros. It's generally self-sufficient because of the way that it installs work, and it kind of fixes itself when there's problems. And we collect and store terabytes of data, and that's the main goal of the system, is just to collect the data. And at the top, we're using Elasticsearch's cross-query mechanism to federate or aggregate all of this data together so we can have a single pane of glass for our NOC, and then we can do very complex alerts that are outside of a single item return and kind of aggregate those together. So the collection loop, you're probably familiar with the way Zabbix works. There's a little bit of spice in here. So we start collection, and all of the user parameters are done in like Ruby scripts or Python scripts, and they have a subroutine that talks out to this factor cache and gets a fact lookup. We will talk about that a little bit later. So it gets some facts back, and it uses those to perform the tests. So it's going to talk to an HTTP website or something like that. And then you have your single output value going into Zabbix, and then we could optionally send stuff back via Zabbix traps. And then also we output a parallel rich JSON doc towards Redis. So Zabbix stuff as normal goes into the Zabbix controlled index here. And then our rich JSON documents go into the Logstash and Elastic for us. And so Cosmos facts are a place to store variables. They're basically a map or a dictionary in Redis, and they always have a TTL, which is really important, and they are accessed by a Cosmos key. Cosmos key looks like this. It has some namespacing information and a version, sort of a bit mask here, and then a primary key that's made up of some of the information about this entity. So we would have a customer ID and then some database IDs and maybe a host name or something like that. We use this, items in Zabbix just receive this Cosmos key as input, and the user parameter scripts use this to go learn information about the test. We do this for several reasons. Occasionally we want to send lots and lots of parameters, and we're kind of limited by the 9-item parameter limitation. We want to avoid unnecessary item destroys. If something in the entity changes that we are testing, we don't want to delete the whole item and all of the triggers just to like recreate it. So we get around that, and then we avoid item key length restrictions, which is cool. So inside kind of looks like this. When it gets printed out into an LLD, it provides some values to Zabbix so we can do filtering and stuff of that nature. So how does the system take on workloads or collection tasks? So we start with a Zabbix template, as you're familiar with. We have a whole bunch of auto registration rules that key off of the host names of the containers that are joining the network. And so they all get their associated templates. So there's a config change in Zabbix, and they end up with an election item and a Reaper item. We load an intent, which is just a JSON feed list, into an S3 bucket, and that is periodically fetched by the core nodes and then loaded into Redis. Once in Redis, the election item can then start to pop things off of joining queues, and that causes a state change in Redis, which associates that entity with that particular agent, and then we end up with LLD there. And so it'll continue electing items off of those join queues until it's full or it runs out of things to look at. And then we can have this Reaper item go off. Since we have new entities, it's not going to do anything right now, but I'll show you later what that does. So Zabbix has this LLD, this giant LLD blob. It consults the template again, and then it renders item prototypes, which cause us to have a whole bunch of tests and user parameters there. And then it just goes off forever since this is, all of the items are run in an active mode. It just continuously collects data for us, which is cool. So let's see, probably be best for me to be over here. So this is what a Feedlist pull looks like. So say we have 9 entities that we're adding to the system, and we have 0 state up here. We'll pull those into the system. All of these fact entries are created, and they have a TTL, which is really important. And then these join queues are populated for the various tests that we have. As the election starts, the precondition is that the worker is not at capacity. There's some algorithm that informs the agent when it can no longer take more work. And one of the reasons we do this is because in the version of Zabbix that we're using, parallel tasks are serial, or active item checks are serial and not in parallel. And so we have to have this limitation. If it passes that, it attempts to pop a task, and then it checks to see if it's already active in the system, if some agent owns that. If not, it records it in its active, or in the active set, and then it records its ownership under the worker set. So you can see here the HTTP worker 1 picked up entity 1 off of the joining queue, and it took ownership of it and it marked it as active. And so the election cycle continues like this. You'll notice that these are not distributed in the same way everywhere, and that's because all of the agents are competing and pulling off of the stack as fast as they can to elect items. And so we've claimed all of the items here, and they will now return an LLD that makes Zabbix go out and tell the agents to start monitoring all this stuff. And so the LLD more specifically is the union of this worker set and this active set. So we have 5 and 6 here, and that will return 5 and 6 as the LLD to the Zabbix server. If we were to take out 6 from this active section here, we would only get an LLD of 5, even though we have 5 and 6 here. And so this is the second iteration of a Feedlist pull. I told you the TTLs are really important. One of the things that this system does is automatically shed work when we no longer want it to, based off of the declarative Feedlist. And so when we do a Feedlist pull, anything that is in the Feedlist gets an updated TTL up here. In our system, it's about 3 days, and a low TTL is considered 4 hours. So that gets there. Join queues get populated again. And then the election cycle runs, and it has noted that everything is already in the system, so it basically throws all that away. So here we have a low TTL, and when that happens, a Reaper is activated, and the Reaper comes in and removes the association with the worker, and that will cause the LLD no longer to return that entity, and we'll stop testing that. And then the fact up here naturally decays with Redis's time to live mechanism. So I have I had videos, but I guess, let's see, are they here? Yeah, so we'll go through this. This is a local environment built on my laptop. So we have all of these queues here, and then we have all of these containers that have joined into the network. And based on this interface, we have discovered, you can see the election item here that runs every 2 minutes in this local dev environment. And then all the templates with the tests. These all get attached by the auto registration rules that we talked about earlier. And they discover their state every 5 minutes or so. They create all these things, including the Reaper, the main test. We have some trigger prototypes here for very easy conditions like HTTP response code changes. And then, let's see. So this is what it renders. It's not like superhuman readable, but like we give it a JSON blob and it just starts collecting data for us, which is sweet. So all of the triggers, and then we'll get to the auto registration stuff here. We'll move on. So this is what all this looks like. It's pretty simple. And then our Kibana stuff, this is just an Alexa top 500 website, and some of the indexes in Elasticsearch. And keep in mind, this is just running on my local laptop, so it's not super spazzy. But these are what the documents look like. You can see that we have the exact Unix command that we fired in the document, which is helpful for a knock. We also have a standard set of all of the facts in all the documents, so it's very easy to thread through all of the various tests, and so on and so forth. And yeah, this is great for our knock because it's not magic, it's not a black box. So that's about it there. Let's see if I can go back. So we like the system because of its simplicity. We can write a wrapper for anything that we want. We do MTRs, we do digs, we do tons and tons and tons of stuff. It's super extensible. It's not a magic black box. We're using familiar utilities here, and it's very easy for our operations team to reproduce any of the results that this system comes up with. It's compartmentalized for fault tolerance. We've distributed over hundreds and hundreds of T3 micros, and we have thousands and thousands of Zabbix agents running containers. So any one going out of service, it doesn't impact us too much. And then with the active checks, we distribute the workload, and it's super easy for us to move this into a Kubernetes environment, which is not currently in. And so wish list. I am pleased to announce I got this already just 10 minutes ago, so that's cool. Parallelism for the active item checks has been something that we've wanted forever. It would be really cool to have a mechanism for distributed item checks across a collection of Zabbix hosts. This basically replaces most of the Cosmos architecture. And then we really liked we would really like to see continued Elasticsearch integration and container development. So I'll skip through these and go to the end. So thanks. You can find me on Twitter, my personal Twitter at hwshadow, or send me an email at p.green@f5.com, or just come hit me up after the show. I'd love to show this to you all. So thank you.